Hello everyone, welcome back to lesson number 22 for BC Calculus. This is where we're talking about optimization, and I've decided that for this particular lesson just to break it up into each individual question just so it kind of gets its own little video. So for example number 1, we talked about how to find the volume of a box, and it's a very classic optimization question. Well, this is also a very classic, I think, optimization question where it talks about a cylindrical can be made to hold 1 liter, which is 1,000 cubic centimeters of oil. It is find the dimensions that will minimize, we left off the E there, but it's okay, there should be a little E here, that will minimize the metal of the cost of the metal to manufacture the can. So just like in the previous video, we're having ourselves a little can right here, and we want to know what is the dimensions that will minimize the cost of the metal of the can. And then they're giving you guys the surface area and they're giving you guys the volume. Well, we want to know what this is. We want to know how to minimize this right here. So taking the metal and replacing it over the can. So you guys can see that this is really surface area. So we're looking for how can we minimize the surface area of this can. So we've already given the surface area of a can, right, a cylinder can, like you see right here, 2 pi r squared plus 2 pi rh. Now, one of the issues that we have with this problem is that, like I said in the first video, you want to get everything in terms of one variable. And so here we have an r and we have an h. So what they did very nicely for us is they gave us the volume of our cylinder as well with a radius and a height, so we can solve for h. And then what we do is we replace this h with this expression. So our h is simply going to be equal to our volume over our pi r squared. Okay? Now, what's beautiful about this is it tells us what the volume is. It tells us that this can hold 1,000 cubic centimeters. So we already know that V is going to be equal to 1,000. So when I rewrite this problem, I can write area is equal to 2 pi r squared plus 2 pi r. I can replace h with 1,000 over pi r squared. And just like in the previous video, I can just quickly simplify this a little bit more. And here we go with this, area will be equal to 2 pi r squared plus, I can go ahead and see that the pi's are going to cancel out. This r is going to cancel with this r. And so I'm left with actually 1 over r times 2,000. Or 2,000 r, 2,000 over r, but that's, I think, the easiest way to do this. So that's awesome. We want to get, when you guys are doing these optimization questions, you want to have the equation that's going to, put all these variables together, and you want to get it in terms of one variable. So that's exactly what we see right here. So now the next thing we need to do is we need to take its derivative. So we want to take the derivative of our area. And so remember that 2 pi is a number, so I'm going to move the 2 down. I'm going to get 4 pi r. And this is in terms of r, okay? So we're looking at r right here. And then this, the reason I read it like this is because I'm going to go ahead and do the plus. I'm going to get to 2,000, and then the derivative of 1 over r is just really going to be equal to negative 1 over r squared. All right, that's a pretty easy thing for us to, to do. And so I'm going to go ahead one more time and do pi r, 4 pi r plus, that looks like a t, plus, minus, actually let's go ahead and do the negative part of that. So negative 2,000 over r squared. And we want to set this equal to 0. We want to set this equal to 0. And so let's go ahead and now solve for r, because that's the best part about this problem, is that we just have to simply solve for r. So I'm going to go ahead and move, and this part, like I said, it becomes pretty straightforward, over r squared. So I just move this to the right. I'm going to go ahead and cross multiply our r's. And so this again is when my derivative, my area, is actually going to be 0. So r cubed is going to be equal to 2,000 divided by 4, which is going to be 500 divided by pi. And so there's only one answer here. So r, when our radius is going to be equal to the cube root of 500 over pi, then this is going to actually minimize, it's going to minimize our actual can. Our actual can. So this distance here will be the cube root of 500 over pi, and then the units here is going to be centimeters. And so that's going to give us the minimal cost for the metal of this manufacturer. Okay, so I think that's pretty good for this video. And again, just remembering, you want to get one general equation, you want to solve for it, the derivative. And again, remember, the derivative, it's a rate of change, right? So you want to make sure that the rate of change is 0, and because that's where you get a minimum or maximum when your change is actually at a 0. So again, going back to why this works in our lesson, if this is actually a rate, right? So at a maximum, we have a rate of change that is 0, and at a minimum, we have a rate of change of 0. So that's why, and for this example, we're looking at the minimum, and there was only one value for R, that's going to be our minimum. And how you know it's a minimum is if you went back up here and did the little table chart thing that we always do, you're going to see that it's going to be negative to the left of this value and it's positive to the right. So students always ask, how do you know it's a minimum instead of a maximum? And so the beautiful thing about minimum and maximum questions is if there's just one variable, it's usually going to be the one that we need to answer the question. Okay, so that is our can question. So we're going to come back in our third video and talk about our parabola question. So I'll see you guys back in the next video.